Good evening, everyone. This is the 12th live discussion session of the course Soil Mechanics Geotechnical Engineering 1. The topic of today's discussion, problem solving session, is Introduction to Stability of Slopes. It's already 5, so I've already started the discussion. Uh, like the previous sessions, this problem solving session has multiple choice questions, multiple select questions, true false statements, and some numericals. This session will be covering only the basics of the slope stability problems, the issues faced during slope stability, and whatever the problems that have been given, it will deal with the basic conceptual techniques on how to deal with slope stability problems in cohesionless or cohesive soils, about the critical height of slopes, and about the various kinds of failures, circular failures in soil or debris slopes. So I've already joined the meeting and I've started the discussion. People haven't joined yet, so I'll start the discussion. I'll start dictating the questions now. If someone joins, they can start writing it from that point. So this is the last live discussion session on this course, Soil Mechanics Geotechnical Engineering 1. And tomorrow there'll be a summary session on the entire syllabus, that is on the entire 12-week sessions that have been covered since the 30th of July. So from 30th July till 15th October, whatever have been covered will be covered tomorrow in the summary session as a part of revision. So I'll now start dictating the questions one by one and give some time. If someone joins, they can start writing the question, and then in the stipulated time given to them, they can solve the questions. After that, I'll be discussing the questions, I'll give the solutions and discuss the concepts behind the solutions. I hope I'm clear. I hope the PPT is visible. So I'll start. Okay. So this is week 12, Introduction to Stability of Slopes. The first question is, the stability number of a slope is a function of. The stability number of a slope is a function of. The options are cohesion, unit weight, height on the slope, or factor of safety with respect to cohesion. So what are the factors basically on which the stability number of a slope depends? Among these factors, one or more can be correct because this is a multiple select question. I'll repeat the question once. The stability number of a slope is a function of. The options are cohesion, unit weight, height of the slope, and factor of safety with respect to cohesion. Okay. Next question. The angle of shearing resistance used in the chart of Taylor stability number is. The angle of shearing resistance used in the chart of Taylor stability number is. The options are effective angle, weighted angle, apparent angle, or mobilized angle. Microsoft Edge is disturbing how much. I'll just switch to for this. The angle of shearing resistance used in the chart of Taylor's stability number is, what is the description of the angle or the definition of this of that angle of shearing resistance? What is the definition as is used in the Taylor stability number chart? Options are effective angle, weighted angle, apparent angle, or mobilized angle. I'll repeat the question once. The angle of shearing resistance used in the chart of Taylor stability number is, the options are effective angle, weighted angle, apparent angle, or mobilized angle. I'll go to the next question. What is the basic difference between toe phase and base failures in slopes? What is the basic difference between toe phase and base failures in slopes? Thus, the main or the significant difference between these three kinds of failures will be sufficient to answer this question. What is the basic difference between toe phase and base failures in slopes? Okay. Next question. The maximum value of stability number is, the maximum value of stability number is, the options are 0.562, 0.562, then 1.261, option 3 0.269, and option 4 0.261. The maximum value of stability number is 0.562, 1.261, 0.269, or 0.261. Okay, next question. For the case of toe failure, the depth factor is, For the case of toe failure, the depth factor is, the options are more than 1, less than 1, less than 0.5, or equal to 1. For the case of toe failure, the depth factor is more than 1, or less than 1, or less than 0.5, or equal to 1. Okay, next question. For the case of base failure, the depth factor is, for the case of base failure, the depth factor is more than 1, less than 1, less than 0.5, or equal to 1. It is the same question as the last one. The type of failure has been changed. I'll repeat the question once again. For the case of base failure, the depth factor is, the options are more than 1, less than 1, less than 0.5, or equal to 1. I'll go to the next question. In the Swedish slip circle method, it is assumed that the surface of sliding is, the options are arc of an ellipse, arc of a circle, a straight line, or arc of a parabola. What is the shape of the surface of sliding that is assumed in the Swedish slip circle method? I'll repeat the question once. In the Swedish slip circle method, it is assumed that the surface of sliding is, your options are arc of an ellipse, arc of a circle, straight line, or arc of a parabola. Basically, it requires the shape of the sliding surface which is being assumed while performing stability analysis with the help of the Swedish slip circle method. While performing stability analysis with the help of the Swedish slip circle method. Okay, next question. Base failure of finite slope occurs when the soil, the options are, is cohesive, is cohesionless, above the toe is relatively weak and soft, that is the soil above the toe is relatively weak and soft, or soil below the toe is relatively weak and soft. This question requires the condition of base failure on a finite slope, and that condition it is with respect to the quality of soil or the properties of the soil. I'll repeat the question once. Base failure of finite slope occurs when the soil, the options are, is cohesive, is cohesionless, above the toe is relatively weak and soft, below the toe is relatively weak and soft. So when the soil should be cohesive, the soil should be cohesionless, so the soil above the toe should be soft and weak, or the soil below the toe should be soft and weak for base failure to occur. I hope it is clear. I'll go to the next question. An infinite slope represents the inclined face of, among the options, which will represent the face of an infinite slope. The options are an embankment, an earthen dam, a natural high hill slope, or an excavation. I'll repeat the question once. An infinite slope represents the inclined face of an embankment, an earthen dam, a natural high hill slope, or an excavation. In other words, which structures among these options will represent the face of an infinite slope? I hope the question was clear. I'll go to the next question. In stability analysis, the term mobilized shear strength is referred to as. In stability analysis, The term mobilized shear strength is referred to as. Your options are shear strength, maximum shear stress, applied shear stress, or none of the above. It means that when we say mobilized shear strength, which among the following stress or strength conditions do we refer to? I'll repeat the question once. In stability analysis, the term mobilized shear strength is referred to as shear strength, maximum shear stress, applied shear stress, or none of the above. I hope the question was clear. Go to the next question. The stability of the upstream slope of a dam has to be checked for. In other words, the stability of the upstream slope is critical during which conditions? The options are sudden drawdown condition, steady seepage condition, steady seepage with sustained rainfall condition, or none of the above. I'll be repeating the question once. The stability of the upstream slope of a dam has to be checked for. The stability of the upstream slope of a dam has to be checked for. Your options are sudden drawdown condition, steady seepage condition, steady seepage with sustained rainfall condition, or none of the above. Or none of the above. Next question. This is a true false statement. Taylor's stability number gives the factor of safety with respect to cohesion only. Taylor's stability number gives the factor of safety with respect to cohesion only. Is this statement true or false? I'll repeat the statement once. Taylor stability number gives the factor of safety with respect to cohesion only. Is this statement true or false? Okay, I'll go to the next question. Yes. A plane inclined at an angle phi to the horizontal at which the soil is expected to stay in the absence of any lateral support is known as. I'll repeat once. A plane inclined at an angle phi to the horizontal at which the soil is expected to stay in the absence of any lateral support is known as. The options are repose line, phi line, natural slope line, or all of the above. Repose line, phi line, natural slope line, or all of the above. I'll repeat the question once. A plane inclined at an angle phi to the horizontal at which the soil is expected to stay in the absence of any lateral support is known as repose line, phi line, natural slope line, or all of the above. Okay, next question. The stability of the downstream slope of a dam has to be checked during. The stability of the downstream slope of a dam has to be checked during. Your options are sudden drawdown condition, steady seepage condition, steady seepage with sustained rainfall condition, or none of the above. In other words, this question means that the stability of the downstream slope of a dam is critical during which of the given conditions, because if it is critical, then it needs to be checked. I'll repeat the question. The stability of the downstream slope of a dam has to be checked during. The options are sudden drawdown condition, steady seepage condition, steady seepage with sustained rainfall condition, or none of the above. Even if in this question more than one option seems to be correct, but this is a multiple choice question, MCQ. So the condition which just exceeds or goes beyond the stable condition, that has to be selected, and not the condition which is highly vulnerable. Only the condition which is just beyond the limiting state, that has to be chosen as the correct answer. Okay, I hope it was clear. I'll go to the numericals now. A long natural slope of cohesionless soil is inclined at 12 degree to the horizontal. Taking phi equals to 30 degree, that is the angle of internal friction or the angle of shearing resistance, as 30 degree, determine the factor of safety of the slope. What will be the change in factor of safety if the slope is completely submerged? This question has two parts. You have to first find out the factor of safety in the natural slope, and then you have to find out the factor of safety when the slope is completely submerged. I'll repeat the question once. A long natural slope of cohesionless soil is inclined at 12 degree to the horizontal. Taking phi equals to 30 degree, determine the factor of safety of the slope. What will be the change in factor of safety if the slope is completely submerged? You have to find the changed factor of safety and the change in factor of safety with respect to its natural condition, if there is any change. I hope it is clear. The inclination is 12 degree and phi is given as 30 degree. Okay, next question. A long natural slope of sandy soil with friction angle of 25 degree is inclined at 10 degree to the horizontal. The water table is at the surface and seepage is parallel to the slope. If the saturated unit weight of the soil is 19.5 kilonewton per meter cube, determine the factor of safety of the slope. The only difference from the last question is that there is seepage occurring parallel to the slope. I'll repeat the question once. A long natural slope of sandy soil with friction angle of 25 degree is inclined at 10 degree to the horizontal. The water table is at the surface and seepage is parallel to the slope. If the saturated unit weight of the soil is 19.5 Newton per meter cube, determine the factor of safety of the slope. I hope the question was clear. I'll go to the next question. A long natural slope in a C5 soil is inclined at 12 degree to the horizontal. The water table is at the surface and seepage is parallel to the slope. If a plain slip has developed at a depth of 4 meter, determine the factor of safety. Take cohesion equals to 8 kilonewton per meter square, angle of friction or phi equals to 22 degree, and gamma sat, this is saturated unit weight, as 19 kilonewton per meter cube. So this is the changed sum. It is a C5 soil having both cohesion and angle of internal friction. And this sum, a plain slip has developed at a depth of 4 meters. I'll repeat the question once. A long natural slope in a C5 soil is inclined at 12 degree to the horizontal. That is, the angle of the slope is 12 degree. The soil is a C5 soil. The water table is at the surface and seepage is parallel to the slope. Like the previous sum, here also seepage is occurring and the direction is parallel to the slope. If a plain slip has developed at a depth of 4 meter from the surface of the slope, it means, when I say a depth of 4 meter, it means from the sloping surface, a depth of 4 meter, a plain slip has developed. So in this case, determine the factor of safety. Take cohesion as 8 kilonewton per meter square, friction as 22 degree, and gamma sat, that is the saturated unit weight, as 19 kilonewton per meter cube. I hope the problem was clear. I'll go to the next question. Yes. Stability analysis by method of slices for a 1:1 slope on the critical slip surface gave the following results. Sum of tangential forces is 150 kilonewton, sum of normal forces is 320 kilonewton, sum of neutral forces is 50 kilonewton, length of the failure surface is 18 meter, the effective angle of shearing resistance is 15 degree, and the effective cohesion is equal to 20 kilonewton per meter square. Now calculate the factor of safety. I'll repeat the question once. Stability analysis by method of slices for a 1:1 slope on the critical slip surface gave the following results. Sum of tangential forces is 150 kilonewton, sum of normal forces is 320 kilonewton, sum of neutral forces is 50 kilonewton, length of the failure surface is 18 meter, effective angle of shearing resistance is 15 degree, and effective cohesion is 20 kilonewton per meter square. Calculate the of safety. Okay, last question is a simple question. A factor of safety of an infinite slope in a sand deposit is found to be 1.732. The angle of shearing resistance of the sand is 30 degree. Calculate the average slope of the sand deposit. So we have given the factor of safety, we have been given the angle of shearing resistance. With these two data, you have to find out the average slope angle of the sand deposit. I'll repeat the question once. The factor of safety of an infinite slope in a sand deposit is found to be 1.732. The angle of shearing resistance of the sand is 30 degree. Calculate the average slope of the sand deposit. I hope the questions were clear. Now I'll start after a while. If someone joins, they can write down the solutions. Around 20 minutes I'll take. If someone joins, then I'll start discussing the solutions after that time. Okay. Okay, uh, now I'm going to start discussing the solutions of the problems that I have dictated a while ago. Okay, so the first question was the stability number of a slope is a function of the stability number of a slope is a function of. So the formula for the stability number is, you can write like this: Sn equal to C by gamma H Fc, where Fc is the factor of safety with respect to cohesion, H is the height of the slope, gamma is the unit weight, and C is the cohesion. So we can write from this formula, we can write a generalized equation like this. If it is a function, then Sn is a function of cohesion, unit weight, height of the slope, and factor of safety with respect to cohesion. So the stability number of a slope is a function of, it is a function of, first of all, it is a function of cohesion. I think then it is a function of unit weight also. It is dependent on unit weight, inversely proportional. It is also dependent on the height of the slope, inversely proportional to the height of the slope. That is true. And also it is dependent on the factor of safety with respect to cohesion. Here also it is inversely proportional to the factor of safety with respect to cohesion. So the stability number of a slope is a function of cohesion, unit weight, height of the slope, and factor of safety with respect to cohesion. So all the options are correct. I hope it was clear. The solution was clear. I'll go to the next question. The angle of shearing resistance used in the chart of Taylor stability number is. The angle of shearing resistance used in the chart of Taylor stability number is the mobilized angle. It is the mobilized angle of shearing resistance. Why? Because the entire friction is what to say, when we apply the shear stress, the entire friction is considered to be used up by the application of the shear stress. Hence, only the cohesion stays in providing resistance to the slope against sliding. So, the angle of shearing resistance or the entire friction gets mobilized, gets used up in protecting the slope against the applied shear stress. The resistance to stability is mainly given by the cohesion. So yes, the angle of shearing resistance used in the chart of Taylor stability number is the mobilized angle. Effective angle is when we subtract the values from the pore pressure and then we get the effective pressure, effective angle. Weighted angle is when there are multiple layers and we find out the average or the weighted average of the slope of the multiple layers. Apparent angle of shearing resistance is not used generally in the stability analysis, and mobilized angle is the friction part which has been used up in covering up the shear stress or the shearing force which has been applied in the slope. I hope it was clear. Next question. What is the basic difference between toe, face and base failures in slopes? So I'll first start with the face failure. So if this is a slope, then the failure surface or the critical slip circle, if it intersects at some point above the toe, then it is called face failure. It's called face failure. Now in the case of toe failure, I hope it is clear by now that this critical slip surface will intersect exactly at the toe. is called the toe failure. It's called the toe failure. In the case of base failure, this critical slip surface goes beyond the toe. It will intersect some point below the toe. It might be at this point, it might be also at this point. So it doesn't matter. Any point beyond the toe, it is called as base failure. It's called as base failure, and this is the basic difference, the mechanism of slope failure, face failure, toe failure, and base failure. The depth of failure is termed as I can say it is as D, or if it is like this, and if the height of the slope is like H, I write it as D naught. So this is also D naught. Here D naught is equals to H, and here D naught is obviously more than H. So the ratio of D naught to H is called the depth factor, which we'll see in the upcoming questions. I have given some questions regarding the depth factor. We'll discuss it then. Okay. The maximum value of stability number is. Now in this stability number question, the maximum value is given itself in the Taylor stability chart. The maximum value is given itself in the Taylor stability chart, and that maximum value that has been given in the Taylor stability chart, it states that the maximum value will be obtained for Sn max will be obtained for a slope angle of 90 degree. And from the chart, for slope angle 90 degree, you can see that the maximum value of stability number, that is Sn max, will be equal to 0.261. 0.261. Yes, this is the correct answer. 0.261. The chart is given till 0.24, but the maximum value is till 0.261. So the maximum value of the stability number is 0.261 for the slope angle, or I equals to 90 degree. Okay, I hope it was clear. I'll go to the next question. For the case of toe failure, the depth factor is okay. So for toe failure, as I have mentioned in the previous question, this depth of failure, if I write it like this, D0, and the height of the slope, this is H, then D0 equals to H. And what is depth factor? Depth factor is the depth of failure D0 divided by the height of the slope. So if D0 equals to H, D0 by H will be equals to 1. Hence we can say that in the case of toe failure, the depth factor, or the ratio of the depth of failure to the height of the slope, is equals to 1. The option 4 is the correct answer. Option 4 is the correct answer. So the case of toe failure, the depth factor D0 by H is equals to 1. Okay. Okay, next question. For the case of base failure, the depth factor is. So again, I'll draw the case of base failure over here. This is the case of base failure, suppose. So again, the depth of failure is this one, D0, but the height of the slope is this one, is H. So we can say that d0 here is more than h, or the depth of failure is more than the height of the slope. So depth factor, that is d0 divided by h, will be more than 1, since d0 is more than h. So the depth factor will be more than 1. So for the case of base failure, the depth factor will be more than 1, that is d0 by h. Depth of failure divided by the height of the slope will be more than 1. In this context, I can also say that in the case of phase failure, the depth factor will be less than 1. In the case of phase failure, it has not been mentioned, I have not given the question, but I can tell you that in this case, in the first case, the second case and the third case I have covered the depth factor. Here d0 will be less than h in the case of phase failure. So d0 divide, so I'll write d0 divided by h will be less than 1, since d0 is less than h. So in the case of phase failure, depth factor will be less than 1. In the case of toe failure, depth factor will be equals to 1. And in the case of base failure, depth factor will be more than 1. So these are also a difference between the mechanism is the main difference, and due to the mechanism, the depth of failure, it is changing, varying in 3 cases, and due to the depth of failure varying, we get different values of depth factors for the 3 cases. For phase failure, it is more than 1. For base failure, it is for phase failure, it is less than 1. For base failure, it is more than 1, and for toe failure, it is equal to 1. It is equal to 1. All right. I hope this was clear. Okay. Next question. In the Swedish slip circle method, it is assumed that the surface of sliding is, obviously, it is, as the name suggests, Swedish slip circle method. The surface of sliding is an arc of a circle, because we are considering over here the mode of failure is circular failure. The mode of failure is circular failure. Hence, the arc of a circle is being considered as the surface of sliding of the soil materials when we perform the stability analysis using the Swedish slip circle method. The answer is, the surface of sliding is assumed to be an arc of a circle. Next question. Base failure of finite slope occurs when the soil. So I'll just draw once again the diagram of the base failure. So if the critical failure surface starts from this and it is extending below the toe, that means what? If it is extending till the toe, then I can say, if it is not like this, if it is extending above the toe, it is extending till the toe. If it is extending above the toe, then the soil in this portion, I can say it is stable or it is strong, hence it has not failed. Okay. Now if it is extending till the toe, that means up till here, then this portion has not been covered. This part of the soil is stable or it is strong, and hence it has not failed. Now in the case of base failure, we know that the critical slip surface, or the critical surface plane, slip plane, it is an arc of a circle and it extends beyond the toe, or it extends below the toe. That means what? The soil below the toe is also weak, it's also soft, hence it is sliding down with the material above the toe also. So in this case, the material below the toe is relatively weak and soft, hence the entire thing is sliding down. If this was strong, then up till here would have slide down. But since this is weak, this part is weak, hence entire it is taking the entire thing with it and it is sliding down. So the soil below the toe is relatively weak and soft. Hence base failure is occurring. This is a weak zone. Weak zone. The soil below the toe is relatively weak and soft. That is why base failure occurs. Okay. I hope it was clear. Okay. Next question. An infinite slope represent the inclined face of. Obviously, an embankment, it has a finite length of finite limitation. Earthen dam, obviously, it also has a finite limitation. And excavation, it is man-made, it also has a finite limitation. But natural high hill slope, it has no limitation because it is up to us to consider the length of the slope in the current analysis as per our own convenience. So we can say that a natural high hill slope generally represents the inclined face of an infinite slope because it continues to an infinite extent and it is not man-made, it is natural. So obviously it is infinite and is not bounded by any, what to say, lateral limitations whatsoever. So an infinite slope represents the inclined face of a natural high hill slope, or you can reverse the statement, a natural high hill slope represents the inclined face of an infinite slope. Okay. Yes. Next question. In stability analysis, the term mobilized shear strength is referred to as. Now, mobilized shear strength means the shear strength that has been used up in application in response to the application of the shear force. In response to the application of the shear force. So whatever the applied shear force is, that applied shear force, in response to that applied shear force, the shear strength that is there will be mobilized. The shear strength present in the soil will be mobilized, but not fully. Only a part of the shear strength is going to be mobilized in response to the applied shear force. So here the shear force per unit area is the shear stress, and that shear stress is being resisted by the mobilized shear strength, or the shear strength that has been mobilized. So the mobilized shear strength is nothing but the response of the material to the applied shear stress. So whatever the shear stress that has been applied, if the applied shear stress is tau and the shear strength is tau f, then from tau f, tau shear strength has been used up in resisting this tau shear stress. I hope it is clear. The mobilized shear strength is referred to as the applied shear stress. The mobilized shear strength is referred to as the applied shear stress. Okay. Next question. The stability of the upstream slope of a dam has to be checked for. The stability of the upstream slope of a dam has to be checked for. So when there is a dam like this is the upstream side and this is the downstream side. The upstream side has water all the time. The downstream side may or may not have water. If it has, it will have to a lower level. This is the downstream side. So when this is the upstream side, this part is saturated. This part is saturated and the water pressure from here balances the water pressure from the outside. Now when there is a sudden drawdown, like there is no water over here, then there will be no force from the left hand side. There will be only force from the right hand side or force from the saturated zone in the upstream slope. That will be critical for the stability of the dam. Hence, the upstream slope of a dam has to be checked for sudden drawdown condition, because at that time the forces from the saturated part of the upstream slope will go unbalanced and the stability will be in question at that time. I hope I was clear. The stability of the upstream slope of a dam has to be checked for sudden drawdown condition. Okay. Next question. Taylor's stability number gives a factor of safety with respect to cohesion only. This is a true statement. This is a true statement. Why? As I've mentioned earlier, the friction gets mobilized. The friction gets mobilized fully. Hence, it is only the cohesion that is left to take part in the factor of safety. So, Taylor stability number gives the factor of safety with respect to cohesion only, because the friction got mobilized in resisting the external frictional force. Okay. All right. Next question. A plane inclined at an angle phi to the horizontal, at which the soil is expected to stay in the absence of any lateral support, is known as. So, in the absence of any lateral support, the slope is a natural slope, firstly, and up till a slope angle of phi, if it stays without failing, then that line, that is that plane which proves that it can stay stable up till angle phi, it's called a repose line, that we all know. It's also called a phi line because the angle of inclination is phi, and it's also called a natural slope line because that is a natural slope that can be considered as stable with the angle of inclination as phi. So, three of these are correct, hence the answer is all of the above. I repeat the question once again. A plane inclined at an angle phi to the horizontal, at which the soil is expected to stay in the absence of any lateral support. So the angle phi, if the line drawn on a plane indicates the slope angle or the slope face in 2D, that line will be called as the repose line or the phi line or the natural slope line, that indicates that up till an angle of phi the slope will be stable. Up till an angle of phi inclination of the slope face, the slope is going to be stable and it won't fail. Okay. Next question. Yes. Stability of the downstream slope of a dam has to be checked during. So unlike the previous case, in the case of a downstream slope of the dam, just a moment. In the case of the downstream slope of a dam, this is the dam, this is the downstream slope, then the downstream slope has water up till this level or no water at all, and the upstream slope has generally water up till a height of up till a greater height than the downstream slope. Now when there is a steady seepage on the downstream slope, then the water rarely rises up till this level. So these forces due to the seepage water the seeping water, it goes unbalanced. If the water is seeping along the face of the downstream slope, then due to the absence of any water on the right hand side, the force on the left hand side, that is the force of the seepage of water, goes unbalanced, and that is a critical condition for the stability assessment of the dam, specifically of the downstream slope of the dam. Hence, the stability of the downstream slope of a dam has to be checked during steady seepage condition. Now, when steady seepage is happening, if there is sustained rainfall, then also the problem will be complicated, because the water may rise, or the rainfall may also lead to the increase in seepage if the water is being absorbed by the dam material. But in that case, if the water rises faster over here due to rainfall, due to prolonged rainfall, then there will be water in the right hand side to balance the forces of the seeping water from the left hand side. The condition might stabilize. But if there is no rainfall, if it is only steady seepage condition, the condition will be vulnerable for the downstream slope of a dam. I hope it was clear. I will start the numericals now. Yes, in the first question, we have a long natural slope. In the first question, we have a long natural slope inclined at 12-degree angle. So now, cohesionless soil, we know for the cohesionless soil, the factor of safety F, that is shear strength by shear stress, that is equals to tan phi divided by tan I. Now, the angle phi is 30 degree, the angle I is 12 degree. So tan phi by tan I, tan 30 by tan 12, will get a value of approximately 2.72. Tan phi by tan I will get a value approximately 2.72. Now in the second part, we have been given that the slope is completely submerged. The slope is completely submerged, then the factor of safety takes this formula, F equals to gamma submerged Z cos square I tan phi divided by gamma submerged Z cos I sin I. Gamma submerged is the submerged unit weight of the material. Now I haven't given the submerged unit weight because this gamma dash and gamma dash cancels each other. Also Z and Z cancels each other. One cos part component also cancels, and then we are left with the same equation like the previous one. Tan phi divided by sin by cos is tan I. Hence the value is same, 2.72. Yes, 2.72. 2.72. Hence, due to submergence, the factor of safety also remains same, because both the numerator and denominator, there is change in both the numerator and denominator, which cancels out each other. So there is no change in the factor of safety if the slope is completely submerged. Point to be noted, we haven't considered any seepage over here. Had we considered seepage, factor of safety would have changed. That is given in the next question. We'll see. Okay. Next question is, long natural slope of sandy soil is friction angle is 25. Yes. inclination of the slope is 10 and the unit weight is 19.5. So in this case, if there is seepage parallel to the slope, then the factor of safety will be equals to gamma submerged by gamma sat into tan phi divided by tan I. Now gamma submerged will be gamma sat minus gamma W, that is 19.5. I write like this: gamma sat minus gamma W. 19.5 minus 9.81. I'll just solve it. 19.5 minus 9.81 is equal to 9.69. To 9.69, it will be kilonewton per meter cube. Now if you put 9.69 divided by gamma sat 19.5 divided by 19.5, and then we multiply by tan phi, that is 25, divided by tan I, that is 10 degree. What do we get? We get a value of approximately 1.314. The factor of safety on putting everything in the formula, we get a value of 1.314. Hence, we can say that when there is steady seepage, because the water table is at the surface, the factor of safety of the submerged slope considering seepage parallel to the slope is 1.314. It is nothing but the previous formula gets multiplied by a factor called gamma submerged by gamma sat. I hope it was clear. Okay, I'll go to the next question. A long natural slope in a C5 soil is inclined at 12 degree. Yes, 12 degree, depth of 4 meters. So here everything has been given. So in this case, for a C5 soil, the factor of safety F is equals to C plus gamma submerged Z cos square I into tan phi whole divided by gamma sat into Z cos I sin I. Because there is a factor of C, that is cohesion, in the numerator, gamma submerged will be considered here. Now gamma submerged will be again equals to gamma sat minus gamma W. Gamma W is 9.81 kilonewton per meter cube. Z will be equals to 4 meter. C equals to 8 kilonewton per meter square. Gamma sat is given over here, 19 kilonewton per meter cube. I, the value of I is equals to 12 degree, and value of phi is equals to 22 degree. Putting all the values in this equation, the factor of safety of this C5 soil slope is equals to approximately equals to 1.44. So approximately equals to 1.44. I'll just give some time because it is a big formula. Okay, so the factor of safety is approximately equivalent to 1.44. Okay, I'll go to the next question. Yes, so here we have been given the sum of tangential forces, normal forces, neutral forces, length of the failure surface, effective angle of shear, and of the friction angle, and effective cohesion. So in this case, we know stability analysis by the method of slices. We can say the factor of safety follows this formula. factor of safety follows this formula. It is CL plus summation of n minus summation of u tan phi divided by summation of t. Summation of t. T is the sum of tangential forces, that is equals to 150. Cohesion is 20. Length of the surface is 18. Summation of normal forces. Summation of normal forces is 320. Summation of neutral forces, that is pore pressure, that is 50. Effective angle of radius is phi is 15 degree. Phi is 15 degree. And okay, there is nothing else. You put everything in the formula, you get a value of approximately 2.88. 2.88. The slope is stable and the factor of safety is approximately 2.88 following the method of slices. So this is the formula which is being followed when analysis is being done with the method of slices. And summation of n is the sum of the normal forces, u is the neutral forces, t is the tangential forces, l is the length of the failure surface, c is the cohesion, phi is the angle of internal friction or angular shearing resistance. I hope it was clear, this formula and the methodology. Okay, last question. The factor of safety of an infinite slope in a sand deposit is found to be 1.732. So it is sand, hence we have to assume that the value of C is 0. The value of C is 0 and nothing is said about the seepage or submergence. The factor of safety value will take a formula of tan phi divided by tan I. Tan phi by tan I. We know the value of phi as 30 degree. We have to find out the value of I. So tan I is equals to tan phi by f, or to find out the average slope or the inclination value will be equals to tan inverse of tan phi by f. That will be, I'll just calculate it, tan phi is 30 degree divided by, it is 1.732. Then if we do tan inverse, we get a value of around 18.44 degree. In terms of degree, we get a value of around 18.44 degree. This is the inclination angle of the slope of the sand deposit. So in this case, since it is sand, we don't consider the cohesion, and since nothing has been said about the submergence or the seepage, we consider the basic formula, that is F equals to tan phi divided by tan I. F is equals to tan phi divided by tan I. Hence, by using the formula and using the tan inverse function, we get a value of approximately 18.44 degree as the average slope of the sand deposit. Okay, so we come to the end of our discussion. I hope it was clear, the solutions were understandable and the concepts were clear. So tomorrow there will be summary session regarding all the live session that has been done by me. It is going to be a 1 hour summary session and it will cover the basic concepts of the previous chapters mainly. Okay, so thank you.